Okay, good afternoon, everyone. Welcome to the RAL seminar. And today, our speaker is Aaron Wan. So I take note of his self-introduction in case I missed anything. So Aaron received his PhD from Penn State University, where he investigated near-surface turbulence and their impacts on the tornadoes. So it's very different from what he's doing here. And after he joined Pacific Northwest National Lab as an Earth scientist, he started to get more interested in the cloud physics. So he began to do simulations related to cloud chamber. And so his work ranges from Cloud-Aerosol turbulence interactions to studies of the atmospheric boundary layer and wind energy. He is broadly interested in turbulence and its impact. So today, he uses tools, for example, large eddy simulation, direct numerical simulations, and machine learning. So today he will be talking about simulating cloud aerosol turbulence interactions in the laboratory. Okay, the floor is yours, Aaron.
Okay, thank you, Cici, for the introduction, and hi, everyone. Today, I want to share with you about my work on simulating the cloud aerosol turbulence interactions in the laboratory, that is the cloud chamber. And I will use large eddy simulations, direct numerical simulations, and machine learning. Because I want to combine several of my papers to tell a story, so I think it's better for me to give you a brief outline. I will firstly briefly introduce my background, my interest in turbulence, and the first project I joined at PNNL, which is ACDC2, which stands for Aerosol Cloud Drizzle Convection Chamber. And in ACDC2, I will introduce why we want to simulate the cloud chamber, which we can perform in the laboratory. Because simulations allows us to reproduce, extend, and interpret the cloud chamber experiments, I will introduce two works. One is on glaciation, another one is on entrainment. We can also use numerical simulations to design a new chamber. I will introduce how we optimize the glaciation coalescence, and we can use it to probably to produce a cloud top in the new chamber. And lastly, I will introduce the challenges I'm dealing with. That is the modeling approaches of the wall flux, or we just call it wall model. We will use machine learning to build a better one for convection cloud chamber. And we'll also do intercomparisons among large eddy simulations and direct numerical simulations. And finally, at the end, I will introduce some follow-up work at PNNL, which is called DREAM2, which stands for Drizzle Representation via Enclosed Atmosphere Measurement Modeling. I never remember the full names. So this is the brief introduction of my background, starting from my undergrad at National Taiwan University, where I studied atmospheric sciences and double major mechanical engineering, because I was afraid I couldn't find a job in atmospheric science. But later, I still like it, so I continued with it and got my master's degree at the same university. And later, I went to Penn State University to study for my PhD, and I graduated roughly 3 years ago. Before I joined PNNL, I briefly served as a part-time software engineer at a startup company, because I was afraid I couldn't find a job. But later, I still like it. So later, PNNL gave me an offer, and I accepted it, and I joined PNNL. And at the end of 2023, I became an Earth scientist until now. Although I spent some time outside of the field, I still feel that many of them contribute to what I'm doing now. For example, when I was studying at the Department of Mechanical Engineering, I found my interest in turbulence. And when I was serving as the software engineer, I improved my coding skills. I learned a lot of coding software, coding tools, and I also improved my typing speed. So I think all of them contribute to what I'm doing, that is simulating the turbulence in the atmosphere. To introduce my work, I think I need to briefly introduce turbulence. It is the instability caused by velocity difference in the space. We can see it from the cup of coffee. If you have ever stirred your coffee, then you know how to make use of it. If you ever experience turbulence in the flight, then you know why it is called instability. If you just put the milk into your coffee and you don't touch it, and you want to wait for the milk to spray throughout your coffee, you may need to wait for a couple of hours. But if you pick a spoon and just stir it, then they will mix just within a second. So you can think of turbulence as a very efficient way to transport those flow quantities. And you can replace the milk with any flow quantities, like momentum and any scalars. And there is one long-standing question in turbulence, that is how to parameterize or model the turbulent flux through the measurable quantities, like the mean wind speed or temperature difference. And this question has been acknowledged by several famous guys, like Werner Heisenberg. He said, "When I meet God, I'm going to ask him 2 questions. Why relativity and why turbulence?" I really believe that he will have an answer for the first. And Richard Feynman said that turbulence is the most important unsolved problem of classical physics. And this is Professor John Simbala at Penn State University. He's the author of this textbook, and I had the opportunity to take his class. He said this, and I took the note. He said, if you can find a universal turbulence model, you will become very famous and probably very rich. But I don't expect that to happen. What I mean is that most of the turbulence model is designed case by case. For example, the wall model for a canonical boundary layer may not be applicable to other kind of flows, like the convection. That is what I'm doing. So improving the turbulence model becomes a continuing effort in the turbulence community. But with the improvement of computational power, now we are able to explore turbulence in greater detail. Here I will introduce 2 tools I use. The first one is direct numerical simulation, which means that we simulate every scale of the turbulence down to the dissipation to heat. If we can do this, then we don't need any turbulence model. But this is super expensive, and most of the time it's not applicable to the atmospheric research. So the second approach is needed, which is large eddy simulation, which means that we simulate large eddy directly. And for the smaller eddies, we parameterize them with the subgrid scale model, SGS model. And the requirement for large eddy simulation is that the grid spacing should fall within the inertial subrange, where the turbulence is supposed to be stationary, homogeneous, and isotropic. So their behavior is relatively more universal and easier to model. But the problem is that near the surface, this inertial subrange will become very narrow. So most of the time, it's not able to have that grid spacing near the surface. And we need another turbulence model near the surface. That is the wall model. And during my PhD study at Penn State, I was mainly simulating the atmospheric boundary layer and tornado. This paper shows that in large eddy simulation, if we use some diffusive advection schemes, they may kill the resolved turbulence, underestimating the resolved turbulent flux, and overestimate the near-surface wind shear. And in the idealized tornado simulation, we have 2 new wall models for it. The first one is implemented by ourselves to include the influence of turbulence memory. Another one is borrowed from the engineering community, which is called thin boundary layer equation. And we found that both of the new wall models applied to tornado will enhance the maximum velocity within the tornado. And after I joined PNNL for ACDC2, I started to simulate cloud within the cloud chamber. There is a cloud chamber at Michigan Tech University, which has been very successful in studying aerosol cloud turbulence interactions. But one limitation of that pi chamber is that it is too small for droplet to grow to big enough for collision coalescence. So they want to build a new one, which is larger in scale, and hopefully the collision coalescence can be observed in the new chamber. And my main task in ACDC2 is to use numerical simulation to assess this new chamber to see how to design a better one to optimize the collision coalescence. So to introduce the cloud chamber, first I need to introduce how it works. This is a schematic of the pi chamber at Michigan Tech University. although the sidewall in the real pipe chamber is usually cylindrical, but in the simulation, we usually simplify it with the cuboid domain. So here I still use it for illustration. There should be a warm and saturated bottom wall and a cold and saturated top wall. So there will be a radial Banach convection, and that is a moist convection. Then according to the CC equation, there will be supersaturation. Then we inject CCN, and there will be the cloud. These are the laser sheet photos taken in the pipe chamber, where we can see the turbulence visualized by the droplet. And when the aerosol injection rate is lower, the cloud is cleaner, and the droplets are less in number, but larger in size. When aerosol injection rate is higher, the cloud droplets are more numerous, but smaller in size. So the first part of my work I will introduce is using numerical simulations to reproduce, extend, and interpret the cloud chamber experiment. The first one is on glaciation of mixed phase cloud. This is the title, Insights from Bulk Model and Beam Macrophysics Large AD Simulation, informed by a laboratory experiment. This was published in ACP last year, and I want to thank the co-authors, Steve, Cici, Mihail, Will, and Raymond. So in the pipe chamber, to have the mixed phase cloud, they need to maintain the mean temperature below the freezing point. So when they inject CCN, there will be the supercooled droplet. When they inject INP, ice nucleating particles, there will be the ice crystals. And according to Wegener-Bergeron-Van Dyson process, when both ice and liquid coexist, the ice will grow and liquid will be reduced. What they want to see is, what they want to test is to see how many INPs they inject can fully glaciate the mixed phase cloud to be a pure ice phase cloud. What they found is that the more INP they injected, the more ice crystals there will be, which is as expected. But they also found that no matter how many INPs they injected, there is always the surviving liquid. So we want to understand this phenomenon, and we use two numerical approaches. The first one is the bulk model, which is like a parcel approach. It solves for the steady state and well mixed quantities within the box. And the second one is LES and beam macrophysics, where LES resolves the turbulence. Beam macrophysics resolves the particle size distribution. And in the result, you can see that the domain is not completely mixed. There is the heterogeneity showing the large-scale circulation structure. And this is the result. The solid line shows the result from the bulk model. The marker shows the result from LES. And red shows liquid. The blue shows ice. And we can see that in supersaturation, water content, and particle radius, both models agree with each other relatively well, except for this part, where the bulk model predicts that the cloud can be completely glaciated. But in LES, there is the surviving liquid, which is like what they observe in the pipe chamber. And if we look at the slice of the domain, we can see where the surviving liquid stays. They stay near the bottom wall, where the wall is relatively warm and moist. So the heat flux and moisture flux are strong there. And it takes time for turbulence to mix them with the domain. So before they are well mixed, they are being well mixed within the domain. The air there is supersaturated, and the liquid can survive there. But we also found that although the liquid survives, the other properties of the LES already follows that of the ice phase cloud as predicted by the bulk model. So in the real atmosphere, maybe we can find some liquid near the cloud base, but the overall cloud properties may like that of an ice phase cloud, and we need to be very careful in distinguishing between mixed phase cloud and ice phase cloud. So here are some takeaways. LES reveals the reason why the cloud is hardly glaciated because of the strong forcing from the bottom. But even without full glaciation, the cloud properties can behave like those of an ice phase cloud. So the threshold for differentiating between a mixed phase and an ice phase cloud needs to be reconsidered. And here I want to briefly share our 2024 ICMW intercomparison case, where we use a lot of different models to simulate this case. And we found that there are some more models that also result in the fall glaciation, including the bulk model and DNS and stochastic model, where they only simulate the central region, so they didn't capture the near bottom region. And this one is a model, LES model with Lagrangian microphysics, but with a coarser grid spacing. So everything within the grid spacing, within the grid cell is well mixed. So it reduces the heterogeneity, or we can say it enhances the mixing within the chamber. And it is, the cloud air is glaciated. Okay, the next one is entrainment. The dual nature of entrainment mixing signatures reveals through the large AD simulation of convection cloud chamber. This one was also published last year in JAS. And the co-authors are Mihail, Finn, Will, Jamin, and Raymond. We are exploring two mixing signatures, two extremes. The first one is called homogeneous mixing, where the evaporation time is much shorter than the mixing time. So when a dry air is entrained into the cloud, it will evaporate the cloud droplets of all sizes locally. And if we measure the statistics of the cloud, we'll see that the liquid water content reduction is reflected in the reduction of number concentration, not in radius. But for another extreme, homogeneous mixing, evaporation time is much longer than mixing time. So the dry air can be evenly mixed with the cloud, and we'll see that the reduction in liquid water content is reflected in the reduction of the droplet radius. So how do they experiment this in the pi chamber? There is a hole at the top where they used to put the sensor into the chamber. Now they pump dry air through this hole, and they place the sensors to measure the droplet size distribution at the upwind, center, and downwind locations. Then they can compare the DSD and decide whether this mixing is inhomogeneous or homogeneous. And this is the result. The different colors represent different locations from upwind, center to downwind. The markers represent different inflow properties, inflow condition, whether the inflow rate is fast or slow, and whether it is warm or it is relatively cool. And they found that under the same inflow condition, the signature is inhomogeneous. You can see that the droplet diameter almost doesn't change. But if they put together different inflow conditions for comparison, the signature looks like a homogeneous mixing because they can see the reduction in droplet diameters. But they are actually results from different inflow conditions. And in aircraft observation, this may result from different inflow conditions because of the different size of the eddies above the cloud top. So they call this locally inhomogeneous and globally homogeneous mixing signatures of entrainment. And we want to see whether we can reproduce this in the large AD simulation. We also test different inflow temperature, different inflow velocity, but we extend the experiment to have different aerosol injection rate. And we also see different grid spacing in LES. And our results show that we can reproduce these locally inhomogeneous and globally homogeneous mixing signatures. In different aerosol injection rate, we found that when the aerosol ejection rate is lower, the mixing appears to be more homogeneous. But when it is higher, or the cloud is more polluted, the signature appears to be more inhomogeneous. And for different grid spacing, we found that when the grid spacing is coarser, the mixing signatures becomes a little bit more homogeneous. And again, because everything within the grid spacing is well mixed. So here are some takeaways of this work. Inhomogeneous signature of entrainment can be studied using large AD simulation and spectral beam microphysics. The locally inhomogeneous and globally homogeneous mixing signature can be reproduced. And the inhomogeneous mixing is stronger in polluted cloud, but the inhomogeneous mixing can be weakened by coarser grid spacing. Okay, the next part, I'm designing a new chamber and its experiment. This one is actually my main task, my main responsibility in ACDC2, which is to design a convection cloud chamber for collision coalescence using large AD simulation with beam microphysics. And this was published in JAMS last year. Again, thanks to the co-authors, Mihail, Finn, Silvio, and Raymond. In this work, we test different chamber design, like we enlarge it or we make it much taller, and we also test different sidewall temperatures. Because in the pi chamber, there is only a single temperature, but that may kill the supersaturation. So we want to see whether we can have different temperatures on the sidewalls to make the cloud collision coalescence stronger. And also we want to see whether we can make how different it will be if we make the sidewall also saturated. For the surface roughness, it's because of our knowledge on boundary layer that the rough surface will enhance the surface flux. So we want to see whether this can also enhance the cloud collision coalescence. And the last one we test is the aerosol injection rate. This is the resulting large-scale circulation in the chamber, and this is the resulting collision loss and collision loss per droplet. In short, we found that a tall chamber is needed for droplets to have enough space to fall and grow to the size for collision coalescence. But because when the chamber is tall, the influence of the sidewall also becomes very significant. And if it has only a single temperature, it kills the supersaturation, according to the CC equation. So they also need to have different temperature and also need to be saturated to maintain the supersaturation. And we also found that a rough wall, it helps. It can enhance the heat and moisture flux, especially the moisture flux. It supplies more moisture, more water into the chamber. So the total liquid water content is higher, and thus the total collision loss. For aerosol injection rate, it depends. It depends on how we want to detect collision coalescence. Because the clean cloud has less total collision coalescence, but a larger mean droplet results in more collision coalescence per droplet. So if we want to detect collision coalescence in a local way, like putting the local camera to capture them, then we may want to have more total collision coalescence. But if we want to observe it through a Lagrangian way, like making the droplet fluorescent and check it, then we may want to have more collision coalescence per droplet. Then the cloud needs to be cleaner. So here are some takeaways. Factors to optimize collision coalescence. We need to have a tall chamber, saturated sidewalls with various temperatures, and the rough walls. And this one is an interesting idea proposed by Finn. This is to generate a stratocumulus-like cloud top in a convection cloud chamber. This was just submitted last week. And I want to thank the co-authors, Finn, Mihail, Steve, and Raymond. We use LES and beam microphysics to test the possibility, and our results shows that it is possible. To have the cloud top, we need to have more flexible way in controlling the sidewall temperatures. In short, we need to have a warm and relatively dry upper section. And the lower part, the sidewalls need to be cold and saturated. The bottom wall needs to be warmer and saturated, but it is warmer than the lower sidewall, but still need to be cooler than the upper part. So the mixed layer will not extend above the interface. And this is the result. We can adjust the boundary layer or mixed layer height. This is the result of 3 meters, and this is the result of 6 meters. And these are the profiles of temperatures, relative humidity, mixing ratio, liquid water content, number concentration of haze, number concentration of cloud droplet. This is the radius and standard deviation of radius. This is the diffusion growth, where we can see the negative values at the cloud top, which indicates the cloud top evaporation. This is the collision loss, the standard deviation or fluctuation of temperature and fluctuation of supersaturation. And we examine the decay profiles and budget within the mixed layer or within the chamber. This is the textbook decay profile. And this is the textbook TK budget. And here are the results from our simulation, where we can see that when the mixed layer is deeper, 6 meters, the TK profile is more uniform compared to that with only 3 meters high. And in the budget, TK budget, we can see that the buoyancy term is the most robust one, which also makes sense because the convection is driven by the buoyancy. And we investigate the inhomogeneous mixing and how it varies with height. Here we use another approach proposed by Young et al. 2021, where they derived the relationship between phase relaxation time and liquid water content. They found that they derived that for inhomogeneous mixing because our radius remains almost the same. So phase relaxation time will be inversely proportional to liquid water content. And if we make the log-log plot of them, we should be able to see a slope of -1 for inhomogeneous mixing. For homogeneous mixing, this slope will be -1/3. And we plot this slope with height, and we can see that the mixing is increasingly inhomogeneous with height, especially near the cloud top. The slope can reach -1 at roughly the cloud top. And this observation is consistent with the in situ observation in stratocumulus clouds. So here is the comparison among different scales of entrainment experiment. In the pi chamber, we pump dry air into the chamber, and we examine the droplet size distribution following the air parcel. In the tall convection chamber, we can examine how the inhomogeneous mixing varies with height. And there is a more natural interface between the cloud and the clean air. And also there is the clean air area where we can put some devices, like we can put a fan, dehumidifier, or some small sensors, which should be fun. And in the real marine stratocumulus clouds, there are more mechanisms, like the large-scale subsidence, stable tropospheric wind, and radiation effects. Okay, the last part is on the challenges I'm dealing with, which is the wall flux. We want to build a new wall model using machine learning, and we also do the intercomparisons among LES and DNS models. This one was published in JAS last year, an investigation of LES wall modeling for Rayleigh-Bénard convection via interpretable and physics-aware feed-forward neural networks with DNS. Thanks to Sean and Mihail. Traditionally, the way to model the surface shear stress and heat flux is through monotopical similarity theory, where it states the relationships among horizontal wind speed, height, stability, surface shear stress, and heat flux. But this relationship is derived under a shear-dominated steady state and horizontally homogeneous boundary layer, where in the cloud chamber, in the thermal convection, it is not shear-dominated, and it is not horizontally homogeneous. There is the updraft here, downdraft there. It is not horizontally homogeneous. So our goal is to build a new wall model for LES for this kind of thermal convection. And our method is to perform DNS to train the neural networks. This is the DNS we performed. Our domain is 1 meter cube, and the grid spacing is roughly 2 millimeters. The bottom top temperature difference is 12 K. This is for training and testing. We perform another one with a more unstable flow, which is doubled bottom top temperature difference. This is for testing extrapolation. Because one concern for machine learning is its extrapolation. Machine learning predicts the result by learning. So we don't have confidence if we apply it to the scenario that it doesn't have experience. So we want to see that whether it can extrapolate. And for training and testing, we filter the length. We filter the DNS data from roughly 3 centimeters to 6 centimeters. That is between these two red lines, roughly falling within the initial sub-range, although it's already very close to the edge, but I still consider it's a good range. And this is the a priori test of monotopical similarity theory. We compare the surface shear stress filtered from DNS, and the same for heat flux. The y-axis is those predicted by MOST if we use the filtered input features for MOST. And we found that our square values are not very good for our thermal convection case. For surface shear stress, there is a peak near zero where MOST predicts that it's almost no surface shear stress. But DNS shows that there is the surface shear stress. And when wind speed increases, the result is getting better. For heat flux, the result is worse. And later I will show that it is because that the result is biased by the wind speed, because this is MOST is derived under a shear-dominated boundary layer. So this is our approach to implement these machine learning skills. FNN stands for feed-forward neural network, and PAFNN stands for physics-aware feed-forward neural network. The basic case shows it uses the same input as those for MOST. The output is the surface shear stress and heat flux. Plus W means that we include the influence of vertical velocity. Plus del P means that we include the influence of pressure gradient force. The physics-aware approach means that we cheat by our domain knowledge, because according to our domain knowledge, we know that there are some power law relationship among the dimensionless parameters, like Nusselt number and Rayleigh number. And if we take the log scale of them, their relationship will become linear, and it will be much easier for neural network to extrapolate. So we use Buckingham pi theory to combine them and put them into log scale. So there will be some kinds of Reynolds number, Rayleigh number, and Froude number, Euler number. And cosine theta is already dimensionless. This theta is the angle between pressure gradient force and horizontal velocity. And the output is the Drake coefficient at Nusselt number. And this is our result. We show that even with the basic input, the R-square value has been improved from MOST from roughly 0.3 to roughly 0.6. And the heat flux is even better. And here we show the sharp value, which is a kind of interpretable machine learning skill to show the importance of the input features. We show that the delta T is the most important input feature for both the surface shear stress and heat flux. And the second most important is the horizontal wind speed. But one interesting point is here, we found that the horizontal wind speed is negatively correlated with the heat flux predicted by machine learning, which is different from MOST. And that is why MOST doesn't perform well for heat flux. And then after we include the influence of vertical velocity, the results are better improved. And we show that vertical velocity is the second most important feature for both output. And it is negatively correlated with both output. And if we take the vertical profiles near the surface, this is the vertical profiles of the wind speed. This is vertical profiles of the temperature. And dotted line shows that under the downdraft, we show that when there is the downdraft compresses the wind speed profiles and temperature profiles toward the surface. So the UdZ and the TdZ above the surface is increased. So the near surface shear stress and heat flux are also increased. But vertical velocity is not included in MOST because MOST is applied to horizontally homogeneous boundary layer. So this again shows that there is no universal turbulence model. Okay, and then after including the influence of pressure gradient force, we found that the result for surface shear stress is again much improved. But the result for heat flux is not that improved. And if we consider the governing equation for velocity and temperature, we should understand why. Because pressure gradient force is included in velocity equations, but not included in temperature equations. Okay, now we can go faster. This is the result of the physics-aware neural network. And this is the basic case where we see that with only the basic input, the result is not very ideal. But after we include the influence of vertical velocity, the results are much better. The results are comparable to those trained with primitive low quantities without this physics-aware approach. And after including the influence of pressure gradient force, it's again much improved, just like that, trained with the primitive low quantities without physics-aware approach. So now we have a question, why do we need this physics-aware approach if it is not better than those trained with primitive low quantities? Because its value is reflected in extrapolation. This is the a posteriori test, the online testing, where we have implemented the trained model into LES and perform again. In the trained case, where the bottom top temperature difference is only 12K, we see that all of the wall models perform relatively well. They can capture the range in DNS. But for the extrapolated case, we show that those trained with primitive low quantities, without a physics-aware approach, they fail to extrapolate because they don't have experience in this range. But for physics-aware trained neural network, they can still capture the range of the surface shear stress and heat flux relatively well. So here are some takeaways. MOST, we show that it is not suitable for the pure thermal convection. And neural networks can capture the importance of the wall normal velocity, which is overlooked by the traditional models. The neural networks trained with primitive flow quantities cannot extrapolate to different flow scenarios, but a physics-aware approach can successfully extrapolate. And actually, this principle can also be found in this AI image. This AI image, I would say it's beautiful. We can see the beautiful cloud in a glass chamber on the table. But if we have the domain knowledge, we can tell that this is not the turbulent structure under this Reynolds number. So this again shows that domain knowledge is important when applying AI and machine learning. AI and machine learning is very powerful and convenient, but they need to be guided by physics. And that is our domain knowledge. Okay, the last one, intercomparison of wall fluxes in turbulent thermal convection chamber, direct numerical simulations and wall model large AD simulations enhanced by machine learning. This was published this year in Physics of Fluid. Again, I want to thank the co-authors, Silvio, Kamal, Hedy, Fan, Mihail, Raymond, and Yunsu. And if you look at this AI image, you may feel that this turbulent structure looks more reasonable because the prompt I used for this one is vapor instead of cloud. I consider this also our domain knowledge. And we used 7 models for 4 different cases. We used 3 DNS, CM1 DNS, SAM DNS, and OpenFOAM DNS. And for LES, we use SAM LES with MOST wall model, SAM LES with the physics-aware neural network wall model, OpenFOAM LES with wall-refined grid, where the grid is refined near the walls. The 4 cases are from simple to complex. The first one is with the adiabatic sidewall. Second one is the mean temperature sidewall. The third one is off mean temperature sidewall, where the sidewall is cooler than the mean of the bottom and top. And the fourth one is the vertical convection, where we have the 2 sidewall as warm as the bottom, and 2 as cold as the top. And this is the result. A little bit complicated result, but this is the sensible heat flux of different models on different walls in different cases. The color represents different models. Different marker shows different walls. And an overall observation is that all models agree well in their trends, but we can also see the spread start to exist after case 3. And one most evident deviation is the red markers here on the sidewall, where it is from same LES with MOST wall model. And if we look at the temperature profiles, we can see that although the wall fluxes have some deviations, the mean temperature looks relatively, it's not too bad, except for case 3, where again the red line stands out. And this is same LES with MOST wall model because it underestimates the sidewall fluxes. So it underestimates the cooling effect from the sidewalls, and the resulting temperature is warmer than other models. Okay, And if we want to look at the distribution, local distribution of the flow properties, we can use case 4 because the large-scale circulation in case 4 is fixed, is controlled by the sidewall. Here I show three models, same DNS, same LES with MOST wall model, same LES with physics-aware neural network wall model. The left half is for the bottom wall, the right half is for the front wall. First column shows the heat flux and temperature, wall parallel velocity, wall normal velocity. If we look at the heat flux, we can see that MOST's wall flux distribution is not very, doesn't look very close to the distribution in DNS. But in the physics-aware neural network wall model, the distribution looks much closer to DNS. However, even without the proper distribution of heat flux, if we look at other flow properties like the temperature and the velocities, we can see that their distribution is actually not too bad. Because if the mean heat flux is reasonable, then advection will properly redistribute those properties. However, for the sidewalls, we can see that if the heat flux is underestimated, then the cold air is also underestimated. And these are from OpenFOAM DNS, LES, and wall-refined LES. Again, we can see that the distribution from LES itself is not close to DNS, but the wall-refined grid can help. It improves the distribution and makes it closer to DNS. So here are some takeaways. The case design is suitable for examining the influence of wall flux on flow properties in various wall temperature arrangements. And if the mean flux in LES matches DNS, advection will properly redistribute the flow properties. MOST underestimates the influence of sidewalls, but the local distribution of flux can be improved by physics-aware neural network or the refined wall grid. Okay, so these are the 7 works I introduced. I led in ACDC2. To be honest, when I just joined PNNL, I had no idea what the cloud chamber is. And when I chatted with my colleagues, like during the lunch, I found that most of them had no idea what this is. And sometimes when I casually chatted with my mentor, which is Mihail, sometimes he said that, well, if this project cannot continue, I will find other things for you to do. So I was kind of worried that I will lose my job, or I'm not sure whether this project can survive. And I kind of hope that I can help this project survive. But after doing this for several months, I found that this is very interesting. It's a very interesting project. There are so many things we can do with the cloud chamber, and many things we can do with numerical simulations. And all of the scientists in this project, they are enthusiastic and they are very nice. I'm always excited about the meetings. And now I'm very glad to see that our effort is fruitful. And last year, I joined the ICMW and ICCP in Korea, and there was also a cloud chamber workshop. And I was very surprised by the fact that so many countries now, they are investing a lot of money on building the cloud chamber. The most impressive ones to me are China and South Korea. They are building the cloud chamber for different functions, different cloud chambers for different functions so efficiently. So what I want to share with you today is that we are not being left behind. So here are a brief introduction of what we are doing at PNNL, the follow-up work funded by PNNL. We are developing different models for simulating the cloud chamber. This one is Pinnacles, which is written by Python. The benefit is that we can easily incorporate machine learning trained components. And this one is Earth, where it has the adaptive mesh refinement and GPU compatibility. And this one is the Observing System Simulation Experiment, OSSE. Sorry for the long title. Inverse mapping of the collision kernel and wall flux scaling in a large-scale convection cloud chamber using knowledge-informed deep learning. The co-authors, I want to thank the co-authors, Teishi, Susanna Burrows, Susanna Glinke, Mihail, and Nasser. In short, we randomly scale the wall fluxes by the scaling coefficient lambda W and collision kernel by lambda C randomly within a certain range. And we perform roughly 500 ensemble simulations of this kind of configuration. And we put the virtual sensors within the domain. Then we use the data from those virtual sensors, like vertical velocity fluctuation, temperature mean fluctuation, supersaturation mean fluctuation, and the statistics from droplet size distribution. Through the knowledge-informed deep learning, hopefully we can map the scaling coefficient that we set at the beginning. And this is our result. We show that this is doable. This is the result trained with all of the sensors, which we show that the bias can be maintained at roughly or less than 1% of the parameter range. But actually using all of the sensors to do this is not very practical in the real chamber because it's expensive and also it interrupts the flow. So we also want to see whether we can do this with just one sensor. We test the sensor Q, which is at the warm corner, and sensor 24, which is at the cold corner. And we show that this is also doable. The result is still very reasonable, very good. So this means that when the chamber is finished, we can use the same approach, the same workflow to map the scaling coefficient for wall flux and for collision kernels. And then we can understand how much we underestimate or overestimate the wall flux and collision coalescence in our previous work. So there's no group photo for Dream 2, so I'll see you using this one. Thank you for listening, and thank you for inviting me to share my results. I'm really glad for this opportunity.